All right, guys, so this is video number 2. We're back with more on chapter 15. Chapter 15 is called lipids. In video number 1, the previous video, we just learned about fatty acids only. Today we're going to extend that into waxes, real briefly on waxes, but then wax esters, a lot on wax esters, and then triglycerides. Okay, so this is our second and last video for chapter 15. Chapter 15 is called lipids or fats. And today we're going to focus on waxes, wax esters, and in the last part of the video today we'll talk about triglycerides. All right, so let me put down the definition of waxes and the definition of wax esters first before we move forward. So we'll do that on page 1 here. Waxes are mixtures of water-insoluble compounds, including esters, alcohols, and alkanes. They're all kind of wrapped into one, and they hate water. They're not soluble in water. Kind of like, have you ever seen surf wax on a surfboard? All right, that's on there to stay as it is, to stay as solid. We don't want it, it's not going to melt off or dissolve into the ocean water, okay? It's water insoluble. But waxes do have their primary function is protection, primarily keeping water in or keeping water out, right? If you ever see ducks in the water, right? The water beads right off of their, they have very waxy feathers. And that keeps water out, keeps them buoyant, keeps them dry, etc. Okay, so wax's primary function is to keep water in or out, and the enveloping word for all that is just protection. Okay, wax esters, definition I came up with is the combination of a fatty acid and an extremely long alcohol. Long chain alcohols have anywhere from 16 to 30 carbons, and they're combined via an ester bond. The phrase here is wax ester, so you would assume we're going to make an ester, and we do. As an example, let's take the 16 carbon palmitic acid. All right, that's a fatty acid. We learned about that in the last video. And now I'm going to draw my alcohol with the OH functional group towards the carboxylic acid of palmitic acid because I want to combine them and make an ester. Now we learned about esterification reactions. All right, that was actually represented on our last exam. But if you remove water, right, and you condense these two together, so we got palmitic acid combining with myricil alcohol, a long chain alcohol, and we get a wax ester. It's important to know that when you're done and you're looking at the wax ester itself, where I have a box around right there, that oxygen, whatever's off of the oxygen there, that came from the long chain alcohol. Whereas the other part came from the originating fatty acid. Because sometimes that ester oxygen, the flat oxygen on the ester, not the carbonyl C double bond O, but the O can be on either side. It's very important to take note of that. And we'll do 2 examples written 2 different ways in just a bit. All right, just some information on wax solubility. Waxes are insoluble in water, of course, because waxes are nonpolar. Water's the most famous polar substance, right? And waxes are nonpolar. They hate water. They're afraid of water. In other words, they're hydrophobic. If something loved water, it would be hydrophilic. But waxes are hydrophobic. They don't like water. But they are soluble in nonpolar solvents. Like dissolves like, right? So if waxes are nonpolar, well then some of the famous nonpolar solvents I can think of, and by famous I just mean common, hexane, gasoline, oil, toluene is one. And then in reference to the oil, I always think about the Exxon Valdez when I was a kid, the giant oil spill up near Alaska. Ducks. I think of all the ducks that passed away in the oil spill. And it says here, wax on the feathers of birds can dissolve. Birds or ducks can dissolve. So if that wax dissolves, it puts their buoyancy at risk and prevents them from staying dry, and they can drown. It's just not a good thing. All right, let's do an example right here, okay? It says, draw condensed structures of the fatty acid and the long chain alcohol. So anytime you see fatty acid and long chain alcohol written together in a sample problem, chances are you're going to condense the two or esterify the two and make an ester. Draw condensed structures of the fatty acid and the long chain alcohol from which the following wax ester was derived. All right, so I need plenty of room to draw this out. Let me get to a new page here. So what I'm drawing right now is actually the product. I'm drawing the product first. This is my wax ester. You see the ester functional group kind of in the middle there. Pay attention to the oxygen, not the C double bond O, but the oxygen that's kind of in the flat sequence. The oxygen is off to my right if I'm looking at my notes. Remember I said, well, that's the long chain alcohol part. So I can start on the far left of the top compound here and write it all out to get my fatty acid. So this is a not 24 carbon, but that's a 26 carbon fatty acid. On the right hand side, whatever is to the right of the flat oxygen with the C single bond O, that is part of my long chain alcohol. So this is a, gosh, 28, 29, a 30 carbon length long chain alcohol. Okay, just FYI, the wax ester I've drawn at the very top is carnauba wax. It's on furniture. Now, here's what I was talking about earlier on the last page. Note, what if we had written carnauba wax, the furniture wax, like this? Here you see how the oxygen is to the left of the carbonyl carbon. Well, that oxygen is where all the long chain alcohol part is connected. So if that were the case, I would have a different fatty acid on top there in that top left box and a different long chain alcohol. So you have to pay attention to the way that the product is offered to you on paper before you can break it down into the proper two reactants. So since the oxygen's on the left in the second one, the long chain alcohol comes from the right, CH3, CH248, CH2OH. Fatty acid comes from the right hand side, so it would be CH3, CH224, C double bond O, OH. All right. Okay, so I got a double line there and a star with a circle around it. This is characteristic of me changing gears or moving to the next topic. And that's what I'm doing right now. The next topic is triglycerides. These are also called triacylglycerides. Examples include animal fats and vegetable oils. When I think of animal fat, I think of a solid. Okay, so I think of lots of saturated fatty acids involved. When I think of vegetable oil, I think of something that's liquid at room temperature, which means there's probably lots of unsaturated fatty acids involved. All right, so I got all that out of that first bullet point. Second bullet point, triglycerides. They're formed when the three OH groups of something called glycerol react with three fatty acids or three carboxylic acids to form a molecule with three ester bonds in it. Glycerol is simply three carbons with an OH on all three carbons. Okay, I'm going to draw that as my fourth molecule. So I've just written right now, I've written acetic acid 3 times. 3 separate acetic acid molecules. The simplest carboxylic acid I can come up with. On the right hand side of the plus sign, that's glycerol. It says 3 carbons with an OH off every carbon. If I were to combine these 4 reactants into one product, I would get a triglyceride. My simplest triglyceride is the one in which the acetic acid is the starting carboxylic acid because it's so small. That's the smallest carboxylic acid I can have, acetic acid. Well, with another carbon besides the carbonyl oxygen. Okay, so you just form, I would have removed 3 molecules of water there as well as a side product. All right, let's do an example to help make some sense of this. So, we're going to write out a bunch of stuff here, and then we're going to combine them into esters. So we're going to be doing esterification reactions, okay? So the first one you see up here is 10, 11, 12 carbons, lauric acid. That little 12 colon O means it's 12 carbon fatty acid, 0 double bonds. So this next one I'm drawing, if I wait it out and wait till it finishes, and then put all the H's in. This is 18 carbons with 3 double bonds. This is linolenic acid, and it would be 18 colon 3. 18 carbons, 3 double bonds. So that's 1, 2, and now I'm drawing my third fatty acid. So let's see which one I draw here. CH3, CH24, CH2. Remember, I have to wait till I'm finished drawing in order to explain to you which one I have, because we're numbering all of ours from the right-hand side where the C double bond O OH functional group is. This is 18,1 oleic acid. And finally on the bottom is my glycerol. My glycerol is like the backbone or the spine. So I'm going to take the 3 OH groups, the 3 alcohol groups, and I'm going to dangle these 3 fatty acids off of them. You can stick, for us, you can put any one of those on any of the 3 carbons off of glycerol. But the product you get is a triglyceride. I'm going to draw that product in just a second. Basically what you do is you take one of the carboxylic acids, hook it up with an OH alcohol, remove water from that, and you make an ester. In this case, a wax ester. All right. Now, this product, which I haven't drawn yet, I'm going to draw it in a second, it's said to be unsaturated or unsaturated overall because it's got 3 wax esters, right? So you got the glycerol backbone and you got 3 esters coming off of it, right? 2 of the 3 are unsaturated. The linolenic part, and I forgot what the other one was, but the only one that's saturated is the lauric acid. All right. So let's draw these guys. Again, you can put the hydrocarbon chains in any order you want. I always make the longer one on the end. So I'm drawing what used to be linolenic fatty acid, linolenic acid. And now I've connected it to my top CH2OH bond. Make my single bond all the way down to the second carbon, the middle carbon of glycerol. And now I just put my smallest one in there. That middle one right there used to be lauric acid, right? The CH3, CH210, C double bond O. Okay, and I've messed all these up. They're supposed to be ester. So I will fix those. Those are actually supposed to be C double bond O and then OCH and then an OCH2. So the way I've drawn them, I've drawn the last 2 as ketones, which is simply not right. All right, so I'll have to redo that one. All right, so a few notes here. This is the last page of our notes today. Triglycerides such as lard, right, room temperature, and beef fat, room temperature. These guys are both solids. Why are they solids? Well, they have saturated triglycerides is what they're made of. So they have all these saturated fatty acids, which means all single bonds. Okay, so it takes a higher temperature in order to melt these guys because all single bonds means those hydrocarbon chains can really get tight. And if you can get the individual molecules close together, it's going to require more energy to melt them. Hence, at room temperature, 25 Celsius or so, they're still solids. They melt at higher temperatures than that. Now, vegetable oils, they're like the Wesson oil you see like in the kitchen, these are liquids at room temperature. These are made of unsaturated triglycerides. In other words, lots of cis carbon-carbon double bonds, which causes a kink. Imagine all these guys kinking all over the place, so it's very difficult for them to pack tightly together. If they're not packed tightly together, well then their intermolecular forces aren't as strong, so we can melt them at lower temperatures than even room temperature, -10 degrees, -16 degrees, etc. All right, so some uses and functions of triglycerides in animals. I've already talked about one, which was protection, protect all their internal organs. We'll talk about that one when we get to it. The first one is to provide energy. All right, when we consume fat, or when we eat fat or stuff that has lard or butter or any type of fatty lipid-like material, these triglycerides or fats, they yield 7 calories of energy per gram. In other words, 7 calories per gram, all right? Versus when we consume proteins or if we eat carbohydrates, we are consuming, for every 1 gram, we're only able to derive 4 calories of energy from it. So if you really want energy for the least amount of stuff that you're eating, you'd want to eat fat because 1 gram of fat provides you with 7 calories of energy. Number 2, thermal insulation and buoyancy. This is the one I mentioned earlier. Some examples are layers of fat in seals and penguins. Of course, these guys have to go into the water, which is cold, but also things like polar bears or a moose. They have tons and tons of fat on their bodies to insulate them. And the third one, okay, is padding, protection, right? These layers of triglycerides protect all their internal organs from outside predators who may want to bite them, or if they're in dangerous situations just in nature. This cushions all their vital organs and then protects them from outside elements. Okay. All right. So that's it for for lipids, chapter 15. You are going to see probably some red oxygens when I go back and fix that last page. All right. So anyway, that's it, and I will talk to you guys soon.